From the ruler to the global positioning system, humans are constantly searching for better and better ways to measure distance. Now, a new method of measurement from the National Institute of Standards and Technology, or NIST, may turn out to be one of the most precise ever. The super accurate NIST system can pinpoint the distance to multiple objects, hundreds of kilometers apart, and define that distance down to a nanometer, or a billionth of a meter. That's 1 million times smaller than the head of a pin. To make this happen, NIST employs a technique called LIDAR, which stands for Light Detection and Ranging.
And it's basically the laser equivalent of radar, which is the radio equivalent of sonar, which is what bats use to locate things by sending out a sound wave. So with laser radar or LIDAR, it's the same idea. You send out light and you look at what comes back to get some information.
To achieve its amazing nanometer precision, the NIST measurement system enhances the power of LIDAR with the help of a device called a frequency comb. What the comb does is give off ultra-short pulses of laser light every 10 billionths of a second. Remarkably, these pulses are emitted at very precise times, with each burst a duplicate of the previous one. The frequency comb gets its name because a series of its pulses appear as a spectrum of evenly spaced colors that resemble the teeth of a comb. It's the precise timing and control of the pulses that make it possible to perform super accurate measurements.
And basically we can take them and bounce them off an object, and because we know exactly what the pulse looked like when it went out, we can measure it when it comes back, and we can measure exactly how long it's been delayed in that time of flight. And then from that we can measure the range to an object.
So what jobs may await the NIST LIDAR measurement system? One possibility is helping ensure the precise fit of manufactured parts for cars and planes. Another potential use of the LIDAR system is literally out of this world.
In the other application that we're excited about would be using these to support the next generation of satellite-based space instruments, where the instrument is distributed among different satellites and you need them all to be in the correct orientation and pointing with respect to each other.
Being able to fly a host of satellites in precise formation may one day lead to networks of space-based telescopes, long-range eyes capable of seeing black holes or Earth-like planets in other solar systems.
Those are very complex instruments and they require a lot of technology, and this would, we hope, maybe be one piece that could eventually feed into that to support that sort of effort.